It's my great honor to give a talk at this forum. I'm Jianping Wang, a professor from the Department of Computer Science at the City University of Hong Kong. In this talk, I will first address why V2x is a key enabler of fully autonomous driving. In other words, what V2x can do to improve the inherent limitations of a single vehicle. Then I will introduce a few technologies developed in my group to make V2x serve autonomous driving and transportation at large better. And last, I will briefly introduce the future research directions of V2x-enabled autonomous driving. The title of today's talk involves two terminologies, V2x and autonomous driving. Firstly, let us take a look at what is V2x. V2x is basically vehicle to everything, including vehicle-to-vehicle communication, vehicle-to-infrastructure communication, vehicle-to-network communication, including vehicle-to-edge server or data center or cloud communication, and the vehicle-to-pedestrian communication. Now let us take a look at what makes autonomous driving possible. Human driving relies on eyes providing perception, brain making decisions, hands and foot executing the decisions. Autonomous driving relies on sensors and perception algorithms providing perception, computing units and planning algorithms making decisions, and control algorithms generating control commands. Ideally, if all hardware and software are perfect, full autonomy can be achieved on a single vehicle without the help of V2x. Unfortunately, this is not the case in reality. Some inherent limitations and uncertainties make it mandatory to have V2x in order to achieve fully autonomous driving. Let us first take a look at the hardware limitation on perception. The video at the left side shows that the white vehicle cannot see the pedestrian walking out from the parked bus due to the occlusion. The video in the middle shows that the white vehicle cannot see other vehicles coming from the right side due to the occlusion of the building. In the video at the right side, the road where the white vehicle is driving is an uphill. The occlusion caused by the uphill slope makes it hard for the white vehicle to see the vehicles coming from north to south, the opposite direction. It would be dangerous for the white vehicle to make a left turn. If we have V2x, V2x can help vehicles see better under such occlusion scenarios. Now let's take a look at the hardware limitation from another perspective. The algorithm stack of an autonomous driving system consists of many interdependent software components. This figure shows that it takes different time when executing a software component on different platforms. Considering the stringent delay requirement, utilizing more resource-rich computing at the edge to accelerate the onboard computation is a viable solution for autonomous driving. Sensors installed on individual vehicles are vulnerable to physical attacks and adversarial attacks. The left two figures show that LiDAR is vulnerable to spoofing attack. Figure B at the right side shows that the adversarial sensor attacks can fool the object detection model. Therefore, many ghost objects are detected. Figure C and D at the right side show that such adversarial attacks can affect driving safety. With the help of V2x, calibration among multiple sensors or even multiple vehicles may be able to detect such attacks. From the software side, autonomous driving relies on perception and prediction models. These models often have their own uncertainties. For example, the surrounding vehicles may not drive exactly as what the prediction model predicts. Therefore, the motion planning of the ego vehicle may not be able to plan a 100% collision-free trajectory. If we have V2X, the communication among vehicles can communicate better about their intention. Now let's take a look at the impact from the environment. Adverse weather, such as heavy fog, rain, and snow, may affect the performance of onboard sensors, such as camera and LiDAR, and also affect the interaction among vehicles. In a hybrid scenario, we have autonomous vehicles and human-driven vehicles. On the adverse weather, human drivers may reduce the speed, which affects the interaction among vehicles. If we have V2X, V2X communication can help vehicles see better and operate better under adverse weather. In summary, the limitation and uncertainties of autonomous driving come from hardware, software, human factor, and adverse weather. Such limitations can be mitigated to some extent by V2X-enabled cooperative sensing, cooperative planning, data calibration, and edge computing. Of course, V2X can enable more add-on functions, such as remote control, remote monitoring, and software update. To enable all these, autonomous driving places higher requirements on the performance of V2X. Now let's take a look at what will be the characteristics of V2X in order to support autonomous driving. This table shows that to support autonomous driving related tasks, such as high-definition map, platooning, remote driving, V2X needs to provide ultra-low latency and ultra-high bandwidth. More importantly, it shall provide performance guarantee. The development of V2X is a joint effort from many companies in different domains. For example, many automobile manufacturers, such as Audi, BMW, Toyota, have made their cars supporting V2X communication. Many mobile operators build up their infrastructures to support V2X communication, and we have a few network protocol standardization bodies for V2X communication. Many telecom companies, such as Qualcomm, Nokia, Ericsson, are developing V2X hardware and intelligent transportation system solutions to support V2X-enabled autonomous driving. We put our work together. The V2X solution stack can be summarized in this figure. In the literature, a lot of work has been done for 5G communication and edge computing. In the remaining part of this talk, I will briefly introduce some work done by my group in network slicing, platooning, and alternative means of networking and communication, marked in green in this figure. Due to time limit, I will only go through some highlights without going into technical details. If you are interested, feel free to contact me. Let us first take a look at 5G network slicing. 5G network slicing is a network architecture that enables the multiplexing of virtualized and interdependent logical networks on the same physical network. The most attractive feature of network slicing is to provide guaranteed and differentiated server performance according to service level agreement on individual slices. IETF and 3GPP have a few network slicing standards covering radio access network, transport network, and a core network. Many telecommunication companies and ISPs are working actively in network slicing for applications on Internet of Things, virtual reality, and a smart grid, and so on. The performance requirements for slicing serving for different autonomous driving functions are different. For example, the network slicing for high-definition map requires that bandwidth should be more than 1 gigabit per second, while the network slicing for platooning requires that 99.99% of packets experience delay less than 15 milliseconds. Correspondingly, the resources required for different network slices are different. For example, the slice for high-definition map requires high bandwidth and storages, since a high-definition map has a huge amount of data. The slices for platooning and remote driving are extremely sensitive with latency and need high communication resources. To ensure the performance of network slices, we need to smartly allocate just the right amount of network resources, computation resources, and storage resources according to the workloads and the quality of service requirements. Although mobile service providers can provide 5G network slicing services similar to cloud service, the current practice still counts on the talent to tell the ISP how much resource they need, which is a typical pay-per-request model. However, the talents usually lack professional knowledge on how much they really need, given the workload and the expected performance guarantee. On the other hand, traditional performance estimation based on queuing theory can only derive the average delay, given the typical performance requirement, such as 99.99% packets delay less than 15 milliseconds. It's hard to derive the amount of resources needed using the traditional methodologies. We have developed a set of tools to help the talents to decide how much to request, given its workload and the performance guarantee, whether to adjust, and if necessary, how much to adjust. The resource allocation we use is based on network calculus, which derives the worst-case performance. With the developed tools, there is still some gap between talents and the mobile service providers. For example, the talents only know what kind of quality of experience they would like to receive. They don't know, in order to achieve such a quality of experience, what will be the corresponding quality of service, which is a network performance metric. The translation between QoE, quality of experience, and QoS, quality of service, is necessary in order for more talents to adopt 5G network slicing solutions. We are working with a Silicon Valley company to provide templates to profile the QoE requirements of different applications. Translation from QoE to QoS, resource allocation, and real-time monitoring of the change of QE and QS. Next, I would like to talk about V2X based vehicle platooning. V2X based vehicle platooning has been considered as a viable cooperative driving approach to improve driving safety, traffic efficiency, and fuel efficiency. A few projects on truck platooning have been launched a few years ago in Europe. The key challenge of platooning is to model the complex system which integrates both communication and vehicle dynamics, and how to cope with the error-prone vehicle-to-vehicle communication. We have proposed a reference model to model V2X-enabled platooning as a cyber-physical system and theoretically explore the relation between communication and traffic dynamics. Next, I will introduce a few works that we have done for adaptive communication to leverage V2X technologies to achieve stable communication in complex real-world traffic scenarios. We'll face a few challenges. Firstly, let's take a look at hybrid vehicle scenarios. In hybrid vehicle scenarios, autonomous and human-driven vehicles coexist. They may take different communication patterns. Therefore, it's necessary for vehicles to adaptively adjust their communication strategies. Secondly, in the complex traffic environment, the inter-vehicle communication is inevitably blocked by vehicles and buildings. It will inevitably cause the channel fading and leads to significant packet loss. And last, in the complex communication environment, frequent communication link disconnections may happen, which leads to rapid changes in the communication topology, interfering with autonomous driving's environmental awareness and impairing their reliability. In all these scenarios, it's necessary to adapt the communication strategies from time to time. Adaptive communication strategy can be passive adaptation or proactive adaptation. The passive adaptation adjusts communication only after sensing the degradation in channel quality. Therefore, they cannot adapt to complex traffic and communication environment in a timely manner. And in this approach, users can only passively accept the communication services. The proactive adaptation adjusts communication before the degradation in channel quality, which requires the communication strategy to learn the hidden traffic and communication patterns in different scenarios and adapt to the complex environment and meet the requirements of different users. What I will introduce next is the 3 strategies we propose for proactive adaptation. The first one I want to mention is adaptive networking. It is to determine which nodes should form a network for vehicle-to-vehicle communication. We adopt deep learning techniques to extract the spatial temporal correlation of vehicle trajectory and network characteristics, and adaptively construct and maintain the network by selecting core vehicles based on the spatial and temporal correlation. The second piece of the work is a traffic-aware MIC protocol. This protocol is to predetermine time slots for transmission to avoid collision. In this work, we predict the same direction merging collision by using the collision prediction algorithm, which consists of the trajectory prediction algorithm and the V2X communication. Once we predict that some messages may collide as two vehicles enter certain communication range, we will proactively reallocate time slots for them. By this way, message collision may be reduced. The last work I would like to introduce is a reinforcement learning-based data dissemination approach to adapt the environment change. In this work, we adopt a hierarchical reinforcement learning framework to address the delayed interaction among communication nodes and apply graph attention networks to handle the rapid change mutual influences among communication nodes. And we leverage math learning techniques to motivate communication nodes to explore stable communication strategies efficiently and collaboratively. We now take a look at the performance of the proposed adaptive communication strategies. For adaptive networking, we can see that our approach can adaptively establish and maintain a stable network for message dissemination. In the figures at the left side, we can see that our solution, the red line, can reach 100% coverage at the earliest time. With the leave of some vehicles, the network coverage of our solution downgrades the slowest. So this can indicate that we can establish and maintain a stable network. For the traffic-aware MAC protocol, so we can see our protocol can adaptively allocate time slots according to the vehicle usage distribution and mobility. From the figures in the middle, we can see that our proposed protocol can improve message delivery rate, throughput, and the channel utilization. For the last work, the reinforcement learning-based data dissemination scheme, we can see that the agents can learn the communication patterns of surrounding vehicles, whether they are driving under cooperative driving or individual driving, and they can adjust the communication strategies timely as the communication environment evolves. Next, I would like to introduce our work on transmission scheduling. The first piece of work is called Age of Information-based scheduling. In the V2X scenarios, a vehicle needs to retrieve information from multiple sources, such as infrastructure, network, other vehicles, and pedestrians. However, the channel resources are limited. On the other hand, untimely delivery of time-sensitive information could lead to safety issues. Therefore, how to take information freshness into the consideration of transmission scheduling is critical. Age of information-centric scheduling have been studied recently in the literature. However, the existing work assumes that the channel is reliable or channel unreliability is a prior knowledge. This is not the case, especially in V2X, where communication channel reliability is very dynamic due to high mobility. We proposed an algorithm to handle age of information scheduling with unknown channel reliability. In our model, we assume that the reliability of a channel is unknown. We first estimate or learn the unknown channel reliability by observing the transmission results. The estimation techniques we use is called upper or lower confidence bound, which belongs to the field of bandit theory and machine learning. Based on the channel reliability estimated, and the AOI requirements, a sampling probability is assigned to every source. In particular, if the channel is more unreliable or AOI requirement is harsher, the sampling probability will be higher for that source. At each time slot, the scheduler draws a source from this distribution to transmit its information. Experiment results shows that our proposed solution can achieve about 18% increasement in throughput compared to the baseline algorithm that also meets the AOI requirements. Our theoretical analysis also proved that we achieved the asymmetrically optimal throughput while meeting the AOI requirements without prior knowledge of the channel quality. At last, I would like to briefly introduce an ongoing work called Age of Event-Based Scheduling. We first take a look at the figure. We can see that massive traffic events are happening every day across a city, but we cannot transmit all real-time surveillance data back for monitoring. We also observe that some areas are hot, where more events happen, while some areas are cold. We may be able to capture more events timely by carefully allocating our monitoring resource, like the frequency of retrieving data from an area. This is why we propose the concept of age of event-based scheduling. After all, what matters is we can timely identify or detect some events, especially some abnormal events. We define age of event as the summation of staying time of all arrived uncaptured events. Under such a definition, if more events arrive or longer time, the events remain uncaptured. The age of events increase. The overall idea is giving the estimated total number of arriving events in an area, we infer the worst case that would happen to an area by assuming that all known arriving events will arrive right after we schedule a source. Therefore, before the next scheduling, the waiting time of events will be the longest. Based on the worst case AOE, we infer the scheduler always select the most urgent area whose age of events in the worst case is a maximum to transmit. This is essentially a weighted round-robin approach. Our current results show that our proposed solution can achieve almost 80% reduction of age of events compared to randomized sampling on the very limited prior information. Last, I would like to mention a few possible directions. Looking forward, there are many exciting opportunities ahead in V2x, such as remote driving, digital twin, smart traffic management, and the intelligent road. They all require real-time and big data communication. In short, AI enables V2x to be intelligent enough to enable fully autonomous driving. Thank you.